Just do a quick introduction to hi to everyone who's joined us today. So our speaker today is Associate Professor Fang-Bao Tian from Unit W, Canberra, and he's an expert in computational fluid dynamic methods for fluid structure interactions and complex flows. So today he's going to talk about flapping wings, and I'm going to pass on to him. Thank you so much, Fang-Bao, for accepting our invitation.
Thank you also for your introduction and for inviting me to give this presentation. And thank you. Good afternoon, everyone. So thank you for coming to my presentation. So tonight I'm going to talk about something about flapping wings. Before that, and I would like to acknowledge my students and postdocs whose contents are shown here today, including students, postdocs, and my collaborators. And I also would like to acknowledge the funding, including IRC, ICM, also DSTG, IIS, and Defense US funds here. Here are the major contents of this talk. It will cover a lot of things, including methods to a few applications. Right. So the first thing we would like to talk about is that why we need flapping wings, or why we study flapping wings. For example, shown here is first one is our eagle, and then the flight is very beautiful, and then all these complex flapping wings. Right. So the particular interesting ones are these, for example, hummingbird and this bumblebee. So the bumblebee, their wings are much smaller than their body. So all these interesting things are observed in nature. Now, so one question we would like to ask is why insects or birds have to use flapping wings, right? So, and then in order to explain these, we show a picture here, this picture here. So this picture, basically the horizontal line is the Reynolds number and vertical line is CL, so the lift coefficient, okay? So when we look at the right-hand side of this picture here, so we call steady flow series. It's like a L4 or these, and the lift coefficient can go to about 2. Okay, it's here. And then when Reynolds number drops, so the lift generated by steady flow series drops significantly, right, like this way. And in order to maintain the high lift, people develop vortex generators and flow control series and all these. When Reynolds number further goes down, and then rotating vane, revolving vane comes in to maintain the high lift, and further when we reduce the Reynolds number, and then we go to insect flying, and we call unsteady flow series for lift generation. Okay, and that's today's major contents here in this region, low Reynolds number region. Okay, so therefore, in order to generate sufficient lift at a low Reynolds number, low Reynolds numbers, flapping wings must be used to explore the unsteady lift generation mechanisms. Okay, so then we look at the definition of the Reynolds number. It's rho density multiplied by velocity, operation velocity multiplied by the sky and divided by viscosity. Right. Low Reynolds number means small scale, so that means here the air or character length is smaller, and also low speed, low density, or high viscosity. Right. Now, in air, actually, viscosity is not that easy to control, right? And what we can control is the velocity, scale, and sometimes density as well. Okay. Therefore, for small scale, for example, birds, insects, their scales are small. Definitely, these are low Reynolds number cases. Another special case is low density, like high altitude space and Martian atmosphere. Okay, So those are normally low Reynolds number scenario. Okay. Now, when we go to flapping wings, one question of what are the challenges here? Okay. So the challenges include unsteady and vortex-dominated flows associated with moving boundaries and complex geometries. That's a little bit special for insect type of flies. Okay. And the flows are highly unsteady and nonlinear, and it's impossible to get analytical solutions for such applications. For some very, very simplified part of wing, we may get some kind of analysis outcome, but in general, it's impossible to get that. Okay, and also most potential or linearized series phi here, they can predict some part or explain some part of the leaf degeneration, but not a whole. Okay, it involves nonlinear fluid structure interactions involving both geometry and physical nonlinearities in structures, and it involves multiple skies in unsteady flows. Okay, another trouble is scaling issues. Right? Currently we don't have scaling rules, general scaling rules, bridging insect birds to MIVs. Such rules are missing, and it's challenging to translate biologic insights into engineering design. Okay, and furthermore, the control part of this system is very complex. Okay, it involves open area control system and closed loop muscle systems. Okay, and therefore it involves complex control strategies for hovering and maneuvering a flight, as well as flying in gust. And the sensor and actuation must operate at high frequencies, therefore, okay, because the flapping frequency is very high. And in terms of experimental challenges, it involves unsteady nature. So the unsteady nature of the flow requires 40 high-speed PIV. That's quite challenging. And the small skies and the rapid motion pose challenges in resolution and accuracy of the measurement. And when we go to compressible flows or supersonic flows, and such cases, those cases, experimental facilities are not available. Right? Therefore, our solutions here are using advanced computational fluid methods with proper analysis and also some specially designed rigors to do the research. Okay. So we get methods. Right, we discussed that the flows are complex, geometry is complex, and the boundaries are moving. And therefore, here we use immerse boundary method to address this challenge. Okay, for immerse boundary methods, the simulations are performed on Cartesian grids, for example, like this Cartesian grids that do not conform to the shape of the boundaries. Okay, therefore, the advantages are it was three, four aspects. The first part is the mesh generation is very simple, even for very, very complex geometries. Right? So, and boundary motion doesn't affect the mesh unless we apply adaptive mesh strategy. And the grid connectivity here is very simple compared to the unstructured mesh. Okay, but associated with this, there are a few disadvantages. For example, we need to apply special technique to apply the boundary condition, and it's not easy to maintain the high accuracy and the conservation law near the boundary, and therefore it's difficult to provide enhanced resolution in the local regions. Okay, so in order to address the last challenge, disadvantage here, we use those geometry adaptive mesh strategies. Okay, and on the other hand, the convention methods, they're based on the body conformal meshes. Okay, For such methods, the grids can be, the mesh can be structured or unstructured, or sometimes we involve multiple scenario, okay, hybrid mesh like this one, structured mesh with the unstructured mesh, okay. And the normal methods include the finite volume method and finite element method, okay. So advantage, of course, for these methods are the boundary condition part is easier to apply, and also it's easier to provide enhanced resolution in local regions. Okay, now the troubles for these methods is that the mesh generation could be very time and resource consuming, and take time, especially when it involves time in evolving geometries. Right? For example, for this whole fly, it could take months to run one simulation. Okay, and also mesh quality and the complexity could be very complex and troublesome. For example, for this case, here is the initial mesh, and after about 20 cycles, the mesh becomes like this way. So that means the quality here in those regions becomes low. Okay, and because our focus is on immerse boundary method, here I would like to introduce a bit of fundamentals of this method. And this method, the basic idea is to introduce a force, a body force, into the Navier-Stokes equation, okay, to implement that boundary condition. Normally, when we say boundary condition here, we say the non-slip boundary condition, okay. And the classic traditional methods by Pascal includes two parts. One is the force distribution, and another part is the density distribution. Now, this method is okay for low density ratio case, very low density ratio case. That means the structure part, the MS structure mass is small, is not too large compared to the background fluid. Okay. And then here, the important part is the delta function. Delta function is a smoothed, like a smooth the delta function. Yeah, okay, that's a traditional methods. And for us, in order to consider higher or larger density differences, okay, we introduce a virtual boundary here, or we call ghost boundary or ghost filament. And therefore here you look at the two solid lines. One is a physical boundary, the other is ghost boundary. Okay, physical boundary directly interaction with the fluid, ghost boundary hides behind. Okay, therefore the interaction between these two boundaries or filaments is achieved by introducing a series of virtual springs like this to connect them. And therefore we can introduce the internal energy here, so or elastic energy for this system, and use a way similar to previous slides here. So to calculate the fluid structure interaction force, okay, here. That's a method. And then for the ghost filament or boundary, we can solve the elastic governing equation. For example, here is a flexible plate, and we use this method to solve that. And it can be applied to flapping seine or seine vane for this method. Okay. And we also introduce similar methods to compressible flows. For example, here we solve the compressible Navier-Stokes equation. And we assume no chemical reaction here. This gas is ideal gas, and we can use high order methods towards the convective term and also viscous term here. And for structure part, we can use mesh-free method, material point method for the structure, or FEGM for the structure solver. Okay, and we use 3D TVD Roger cutoff method for time discretization, and similarly we use delta function here to implement the immerse boundary method, and we introduce modified ghost fluid method for level set to handle the shock near the fluid structure interface. Okay, so this is a compressible immerse boundary method, and we can see that delta function here, the accuracy is low, but it works well for these compressible, for lots of compressible flows. That's interesting. And we also implement the IBMS immerse Boltzmann method in lattice Boltzmann method, for example, here. And we apply different models, different lattice Boltzmann models, and including single relaxation time, multiple relaxation time, and lots of other models here, as shown here. We also introduce the multi-block adaptive mesh here, okay, as shown like this way. And we implemented large area simulations. A few different models here is just a simplified model here, and we implemented all model for turbulent spinal layers, as shown here. Okay, that's a IB LBM method. And this method we developed for AIS, Australian Institute of Sports. We call this solver super sport flow. So if you from QUT, some of QUT students using this solver for sports related research, and it's just recently released to sports agencies for their modeling. Okay. And now, so the question is how or why this simplified delta function, this method works. This method works. In order to explain this, I use a heat transfer equation, okay, to explain this. And for example, this is a domain, like a solid domain steady, and then the heat, there's a temperature here, it's the top boundary temperature 100, and other boundaries we implement 0 temperature. Okay, so generally, if there's nothing inside, and for this one, we can use FVM or whatever method to solve that. For example, if we use FVM to discretize this domain around 4 control volumes here, around node 1, 2, 3, 4, we get 4 equations here. Okay, and then we can solve this equation by using whatever method, and we get a solution. That's a general method here. Okay, now, if we say we want to use immerse boundary method to implement a boundary condition here on node 1 to 50, for example, okay, like this. We introduce that similar to the delta function. We introduce this Q here. Q is a heat source similar to force in Navier-Stokes equation. Okay. And then this alpha H square is 100, and then we similarly develop that control volume equation. We solve that equation, we get the solution of this one. Okay, you can see that T1 here is 49.59, and our target is 50. It's very close. And we can increase this feedback coefficient to get more accurate outcome. Okay, now, when we look at this equation here, and this alpha here, it behaves more like a Lagrangian multiply. Okay, alpha behaves like a Lagrangian multiply here in the system. That's a background why it works well in such systems. Okay. And here are a few comments for this method. And if firstly, it's very important to design a proper delta function for the interpolation between 2 meshes, the structure and the background fluid mesh. Okay, and here's some examples, yeah, shown here. And it's crucial to choose the values for the penalty parameters, alpha and beta. Okay, so my best student, Qiu Xiang, did a very good job here in this paper, discussing how to design alpha and beta. And also in this paper, Gernstein's 1993 paper, they also have a very careful discussion here. Okay, and explicit immerse boundary method is sufficient to achieve the long no slip boundary condition for most flows. Okay, for most of the flows, given that the integration is properly applied. I will discuss this a little bit more later. And the effective boundary location is X, capital X, where the integrated velocity was calculated by the following equation. Okay, that velocity should be close to the ghost boundary velocity. Okay, so the fluid volume leakage or velocity error could be a concern for closed boundaries, such as flexible tubes or the capsule's blood cells. Okay, we will discuss this a little bit more later. And the above mentioned IBM is based on the smooth delta function, which is dependent on the mesh spacing and thus generally just a first order exact accuracy. Just generally it's first order, but it works well for many compressed flows, and we applied to like acoustics generated by flapping vanes, supersonic flows, and turbulence flows, all these. Okay, and for velocity penetration here, so I show a few examples here, and people report that they observe this penetration here, velocity penetration here, and there's a few reasons. Okay, so at least there's three major reasons. One is DS is not small enough. Okay, so the correct setup should be roughly half of DX background of fluid mesh. Okay, or the feedback coefficient is not large enough. Okay, and we need to use large value. And sometimes their time integration has a 0.5 or 1 dt delay in velocity correction. Okay, and my student again Chiu Xiang designed a few algorithms. The first one is people is the algorithm normally used by other people in the reference. We can observe that velocity penetration around the cylinder. Okay, and then we designed two other methods, and this one you see that the outcome is very good. I just skip the details. Okay, so and then another one iterative feedback IBLBM, and it's even better. And this method, the good one, the advantage of this method is that it can or we can use lower feedback coefficient to achieve numerically stable simulations. Okay, that means it's more powerful. Okay, and then for now, so the question of whether this sleep velocity error is important or not. Okay, so for external flow, we use cylinder here, and when we look at those data, okay, when we look at those data, and it shows that this sleep velocity error doesn't matter. Okay, but when we move to classical channel, so for example, like this, okay, a small error here, when you look at the velocity here, a small error like 1% or 2% could introduce a huge error in the deformation of this channel. Okay, the error could be 20% or higher. Okay, that means for external flow, mostly external flow, like flow of cylinder, sphere, it doesn't matter. For internal flow, it could be an issue. Okay. All right, there are other methods like sharp interface method, and we use interpolation, high order interpolation to correct that velocity period. I just skip the details of this method. Okay. Okay, when we go to FSI, then we use partitioned FSI. Okay, here, and these are the details. So basically, the structure solver and the fluid solver, they are solved independently. Right? When I say independently, that means when we solve fluid mesh, we ignore fluid. When we solve fluid mesh, we ignore structure mesh, but we consider the interactions through the force and the velocity in the position. Okay, that's just this kind of method. Okay, to make sense easier, and if we want to strengthen the strong or implement the strong coupling, and we just do the iteration. Okay, we use the iteration to achieve that. All right, here's just briefly the experimental facilities. Okay, we have a low pressure chamber to mimic the Martian atmosphere. Okay, and I just skip those details. And this one is a water tunnel water tanker. Okay, so for flapping vent facilities. Okay, now all these are our methods. Next, I'll go to some applications. Now, when we go to flapping vent, okay, and when we talk about high lift generation of flapping vent, the major part or the important part is the vertical structures around the flapping vent, for example, as shown here, okay, and we can see the leading edge vortex, this part, LEV, a leading edge vortex part. It's I think it contributes most of the lift, right? And we have tip velocity and tip vortex and trailing edge vortex, and spin-wise flows. All these sometimes spin-wise flows can contribute to the stability of the leading edge vortex. Okay, so the near field vortex flows determine most part of the forces or lift forces of these flapping winds. Okay, and they affect the pressure distribution and the momentum exchange between or near the body. Okay, and thus determine the forces experienced by the wind. Okay, now therefore when we consider geometries, kinematics of all these, we actually try to control, guide the local momentum flux, modify the vortex distributions, stabilize leading edge vortex, and adjust the force center, or synchronize the motion and configuration of the winds with near field flows. Okay, so that's a general idea. Okay, now when we consider different geometries, for example here, first the Reynolds number actually measures the, like I just said, as is determined by the operation velocity scale of these. And here, if we keep everything the same, but just change the operation velocity, and we can get different Reynolds numbers. Okay, and when we look at these outcomes, first, when we increase Reynolds number, for example, we check this first line of left-hand side picture. Actually, LEV, leading edge vortex strength increases, and it's saturated at large Reynolds number. Okay, like Reynolds number 1000 or beyond. And if we further increase the Reynolds number, and the leading edge vortex just loses stability. Okay, and when we increase this R1 actually measures the area center of this spin. Okay, low R1, for example, this is low R1, so that means the area is distributed near the or closer to the wind root. Okay, here. And this is a medium R1, and this is a high R1. Okay, increase R1 to increase the suction area. For example, when we increase R1, and the low pressure we call suction area increases. Okay, and therefore all these together determine the lift or power economy of this flapping wind. Okay, as shown here. So when we increase the Reynolds number, CL increase, and power economy increases as well. Okay, and when we increase R1 here, the power economy decrease a little bit, but lift increase a lot. Okay, so that's just the case. Okay, so we further check the aspect ratio here. Okay, so we consider aspect ratio from 1.5 to 6. Right. So the major outcome is that increase the aspect ratio, and when we increase that, it destabilizes the leading edge vortex. So for example, when we look at this line, the vortex, leading edge vortex here, again, when we go from this one to this one, this part, near the vent tip, the LEV loses its stability. Okay. And therefore, if we look at this and we increase that, when aspect ratio is lower, we can increase the power economics slightly, but if we further increase that to higher aspect ratio, actually the power economic decreases. Okay, that's a major outcome for this. Okay, now for these kinematics, if we provide a little bit of control strategy to the flows around the wing. Okay, so this work was done by my best student Bruce. Right. So here, this is incoming flow here, and then near the trailing edge, we apply a flow control here. Okay. The idea here is that. So I just directly look at the tip vortex. Okay. So the vortex near the two ends. Okay. So with the flow control, okay, we actually increase the tip vortex strength. Okay, you look at the blue and the green lines in this picture. Okay, and how that could happen? So this actually is enhanced through the velocities at two ends. Okay, so with that control, and we fit fluid into TV through two ends. So as you can see, these velocity profiles here, and this to increase the lift generation. Okay, that's a brief outcome of this piece of work. All right, that's the geometries and kinematics. Okay, so as we know that the veins are flexible, the deformations. Okay, so complex deformations. And when we can see the flapping veins, we introduce more parameters like density ratio, or we call mass ratio, structured fluid mass ratio. Okay, and the frequency ratio, the ratio between the flapping frequency and the natural frequency of the structure. First parameter, the M star, measures the structure inertia to the fluid inertia. And second one is measures the input energy and the initial internal energy. Okay. So when we change the frequency ratio and we look at the thrust lift power economic, and we found that in the medium region, so medium flexibility, we observe optimal lift, okay, and also optimal thrust. Okay, we also have much better power economy for in terms of thrust, but we can maintain the lift economy for a while. Okay, that's a major outcome. So this outcome is determined by the interplay between the inertial forces and the elastic forces. Okay, and this can be applied to 3D as well. For example, when we introduce the geometries, all these, and if we introduce the medium flexibility, and we can see that this red line is a flexible wing, and we have larger lift and larger power economic. Okay, that's this one. And this one you can see here a little bit more introduction for this is that we have veins around the wing, and when we consider different geometries, right, we use a Laplace equation to map these shape with the original design here. Okay, so that's just a small tricking here. All right, so now if we look into the mechanisms of this, of the effects of the flexibility, and we use a simplified model, and we assume all the flexibility, okay, is reflected by the torsional deformation or torsional spring near the or on the rotational axis. Okay, and we consider the flexibility. In this case, we introduce CH number to measure that, and we consider R1 as well, right? And when we look at that, and you can see that optimal CL, left picture is CL. Optimal CL is near the point of CH of 0.1 and high R1, but the highest power economy is near the CH of 0.2, but medium R1 value. Okay, now why they're optimal here? Okay, we found that in the optimal performance or during that optimal performance, there are few synchronization. So, for example, the anti-synchronization of the pitching elastic power and the pitching aerodynamic and inertial power. Okay, and also nearly in-phase synchronization of flapping aerodynamic power and the total input power of the system. Okay, this sounds not that easy to understand. However, kids know how to do so. So if we look at this, okay, there's no big difference between this fin and this flapping fin. So unfortunately, it needs professors and PhD students, postdocs to work on this. Right? But kids, they can do well on that fin. Okay, so when we go to disturbance part, so for example, during the flapping fin, we introduce the vertical velocity here, and we can see that generally CL and CD are proportional to the disturbance, and there are exceptions here. Okay, this exception is due to the local effective angle of attack changes, okay, caused by local flow here. Okay, that's just the mechanism behind. And when we introduce flexibility, and it could improve the lift, okay, or lift to drag ratio here, okay, especially for example, this one and the red one, the medium flexibility has a high lift, okay, and for higher flexibility, we have higher CL to CD ratio, okay. That's the aerodynamics part, okay, and an incompressible aerodynamics part. When we go to high speed, okay, so and consider the roles of compressibility, okay. For example, for similar flapping fin, we run them over Mach number from 0.2 to 1.4, and then we put lift together in this picture. Okay, so from this picture here, we can see that when the Mach number is less than 0.6, okay, the lift doesn't change a lot, okay, when we change the Mach number, right? But if for the low res number cases, it slightly decrease, okay, and for high res number 1, it's slight increase for some cases. But once the Mach number goes beyond 0.6, then CL, the lift coefficient, mean lift coefficient, decreases with the Mach number. Okay, and we call this 0.6 or slightly larger or smaller than 0.6 as a critical Mach number. Okay, so when Mach number less than 0.6, there's no shock wave everywhere, okay, but when Mach number goes beyond 0.6, we can observe local supersonic, local shock waves. Okay, and therefore, the conclusion here is that compressibility has a negative impact in fourth generation of flapping fins. Okay, this conclusion valid for different vanes, different res number, different angle of attack. Okay, as listed here. Now, the question is how we quantify this impact. Okay, here we list out the lift for all these cases. Okay, and when the Mach number less than 0.6, they just follow that general rules as we observed in incompressible flow. And beyond that, CL has a strong, CL is dependent on Mach number. So when you look at the function and Mach number appears when it's beyond 0.6. Okay, and we consider, we organize all those contributions of each term, and we develop a scaling law here. And all simulations, I think, follow this rule pretty well here. And when real number is higher, or sorry, when Mach number is higher, so that the flow is supersonic flow, the major effect is that the leading edge vortex decrease a lot. Okay. So that's a mechanism why supersonic flows has a negative impact on the lift generation. Okay, and similar conclusion can be applied to flexible winds. So when you consider flexible winds, for flexible winds, there's a new phenomena because the elastic motion. Okay, so we observe a secondary shock wave here. Okay, or if you look carefully here, okay, it has negative contribution to the wind to the lift generation. Okay, and when we consider the whole wind or the whole insect here, and we observe quite similar thing. Beyond that, and we observe that we also introduce the slippery velocity due to rarefaction. Okay, so it's measured by Newton number here. Okay, so when we introduce rarefaction, the rarefaction actually increase the rarefaction decrease the lift contribution a little bit to the flapping wind. So, for example, as shown here, this line here, and viscosity here has a negative contribution to the lift generation. When we introduce the rarefaction, it reduces that negative contribution. Therefore, overall, the lift increases a little bit due to this rarefaction. Okay, so if we look at this, and we increase that Newton number, lift over the total lift increase a little bit. Okay, not much, but a little bit. Okay, that's the full insect, right? Okay, now, so if you remember that in the beginning we talked about the lift generation for steady aerodynamics, rotating wind, flapping wind, all these. We mentioned that when Wales number is very low, we have to use flapping wind. And here we compare the rotating wind and the flapping wind for very low Wales number. Okay, Wales number, I believe in this case is just 200. Okay, and here the first line is flapping wind. Here the vertical structure. Second wind is rotating wind. Okay, and when we compare CL here, lift generation. Okay, for lift generation, rotating wind is smaller than general flapping wind. Omega star equals 0 means it's rigid wind, then rigid wind and flexible wind. Okay, but when Mach number is very high and their performance is close. Okay, the conclusion is that so the flapping wind indeed is better at low Reynolds number, low Reynolds numbers. Okay. Okay, last bit is about the acoustics. Okay, I go through these a little bit more quickly because I can see that we already 45 minutes already. Okay, so acoustics is very important. For example, we hear lots of noise for mosquitoes, some sounds generated by pigeons, and also quiet flight by owls. Right, so. And these technology might be used to UAVs or wind turbines and beyond. Okay, so quickly, so for the flexible wind here, okay, when we tune flexible wind and also tune the pitching angle, all these, and we observe that. Okay, so when we increase the pitching angle, the vortex sound source shifts from dipole type of source to quadrupole type of source, okay? And flexibility shifts the sound towards the downstream side a little bit more, okay? That's a simple conclusion for this application. And we consider two winds together, okay, two flexible winds together. And we can tune their phase differences, okay? And the conclusion is that phase differences affects sound. In phase motion, so in phase motion strengthens sound generation, and anti-phase decreases sound generation. Okay, if you look at the sound pressure contours, left hand side one is the in phase flapping, and right hand side one's out phase flapping. Okay, and why this happens? Because we found that the far field pressure is proportional to the lift change, okay, the change of lift force. And because far field, that means second term here is very small. Like the major term is the first term, and therefore for in phase flapping, that means CL of two winds, they're in phase. The total force becomes larger, right? But if they are interphase and they cancel each other, and therefore the far field sound pressure decreases. Okay. So if we go to 3D conditions, okay, so this is the work of my best student show you, okay. So we introduce the trailing edge serrations, okay, and simply, so the conclusions that when they kite, so the wave number is 8 pi, and the height is very large, so 1.5, height is this height, okay. And the average sound power level is reduced by up to 6.8 dB compared to a plain or the regular trailing edge one, while CEL is maintained. That's a major conclusion. This is because that the serrations altered the tip vortex here. Okay, so if you look at the flow field tip vortex here, so the tip vortex for the serrated trailing edge one is much smaller. Okay, the strength is much smaller compared to the regular one here. That's a mechanism behind. Okay. And when we introduce these to the pitching L4 in the heaving L4 in the pitching L4 in the incoming flow. So, and when we introduce this trailing edge serration, and it reduces the average spin-wise coherent fluctuations, and therefore reduce the average surface pressure force, okay, to reduce the sound level. Okay, that's a noise reduction mechanism for this case. Okay, now we know that LEV is very important for force generation. Okay, and then the far field sound pressure is related to the force change. Okay, therefore, my best student show you build a connection between the far field pressure and the pressure fluctuation on the wing, and then connect the pressure change on the wing with the vertical structures here. Okay, and based on this, we can build a scaling law for the sound strength here. Okay, so this is the scaling law for the sound pressure, far field sound pressure, and then we put them here, and this work introduces this, and also in another work we found that the sound pressure and the pressure force change, okay, for a similar trend. Okay, that this work. If we consider compressible flows, okay, if we need to consider pressure, this sound acoustics generated by supersonic flapping winds, we need to apply the nonlinear acoustics. So, for example, as shown here, okay, we need to include this, and the conclusion is that for the second harmonic frequency shifts the profile from a quadrupole source at low Mach number, like Mach number equals 0.6, to a hexapole sound source, okay, like Mach number is 1.4. Okay, that's our latest outcome. Okay, just published, I think, last month. Okay. Now, this is the acoustics. Okay, now what's next? So the question, what's next? So I mentioned that LEV, the strength of the LEV decreases in supersonic flow or even disappears, as shown here. Okay, so this bumblebee, like left hand side is subsonic and right hand side is supersonic. Like supersonic, you can see that LEV almost disappeared, and also therefore the CL lift coefficient is very small. Okay. Now this gives us some kind of thought regarding how to control or stabilize LEV in highly compressible flows. There's a huge potential to increase that lift generation. Okay. And also in the future, we need to consider mechanisms of biological responses to complex environments like turbulence flows, takeover purge, or threats of threat avoidance. All these. Okay, we may need to incorporate the metabolic process, natural control, vision, sensing, all these together to understand more. And we may need to develop a more general scaling laws for both aerodynamic forces and acoustics. And regarding numerical methods part, we may need to develop a more efficient, accurate methods, such as compressible LBM or low Reynolds number compressible turbulence modeling. We also needed to develop better experimental facilities for flapping wings or FSI in supersonic flows. Okay, so actually that's my talk. I don't put a conclusion here, just because that this field so far I don't see a conclusion at all. Okay, thank you. I'm happy to answer questions or listen to your suggestions or comments.
Thank you so much for the very interesting talk. From the audience, if anyone has questions, comments, please feel free to either speak up or you can also type in the chat.
Let me try to no, that no.
Hello.
Uh,
I have a question regarding, in your simulation, you might have considered the main body as stationary. What if the body itself with wings, if it is moving, like in actual scenario, it moves upward, for example. So how does it affect?
Actually, the interaction between the body and the wing, you're asking the interaction between the body and the wing, right?
The body itself, if it is moving with respect to the fluid domain or computational domain.
Some cases we have that. For example, if I show that, let me have a look. I have a video in the beginning introduction part. For example, this one, the body is moving as well, the whole body. Actually, the body part, the contribution to the total force is small compared to flapping wing. Probably just because the unsteady nature of that wing. If you look at the velocity of the body and the wing, the velocity of the body is much smaller compared to the wing. But
So it's
this is a
negligible.
new, yeah, this is a new field again. So because sometimes the interaction between the body and the wing can affect the vent root vortex structures, and then this affect the lift generation significantly. I think Professor Zhong Yang discussed this in his 2009 paper for locust.
Okay. And I have one more question. The vortex shading part, is it always periodic, or is it always, I mean, at the same frequency as flapping wing, or is there any other frequency? I mean,
Yes, so basically, I believe the high frequency or these just because the damage of the vortex structures in the interaction of the vortex structures at a low Reynolds number, I think the frequency is the same. But when we go to high Reynolds number, and when we see the vortex interaction and also tip vortex breakage, the high frequency modes coming out. And
okay.
this also reflected is reflected in the acoustics part. For example, if I go to these slides, can you see my screen?
Yes, sir.
Yeah, yeah. So, for example, these are just different frequency. No, not this one. Sorry. So probably here. So this one. So just different frequency of the acoustics. Or let me show another picture here. So this part, for example, we have basic frequency and double frequency. We can see those interactions, multiple frequencies coming out. Okay.
Okay.
But
Thank you, sir.
for low Reynolds number, low Mach number, it's just one single frequency. Second frequency is very weak.
Okay. Thank you, sir.
Have any other questions?
Sorry that tonight I covered a lot of different things, and some of you might not able to catch up everything. So if you have any questions regarding our research and all this and that, just feel free to contact me or contact my students. Right. So here I believe some of you already know some of them. Maybe not all of them, but some of them. Right. So today, for example, I cover the work by Shavy, this one, and Bruce, this one, Nathan here, okay, Li Wang here, Ryan Qiushang here, okay, some work by Sudan as well. Sudan, I didn't put Sudan here. Sorry for that. Okay, Sudan and also Shantanu here. Okay.
Sir, if no one is asking, I have one more question.
Yes, no
Suppose
problem.
for a non-flexible structure, if I want to start something, like how do I collect the data? Is it only from PIV cameras, or is there any other, I mean, method? I mean, any textbook or paper to follow?
Uh, if you wanna work on that or
Yeah,
because
actually, I work on it's a biofilm uh, in a flow. So the
yeah, so
biofilm sometimes move with flow.
yeah, so those models, that's everything, right? So for example, for the rigid flapping wings, we got those first part is the kinematics part, right? Kinematics part is just a generic kinematics based on the measurement of insects or this type of thing, and people researchers summarize all these things together, and we use that generic motions or kinematics. Okay, when you go to flow field, there are two things. One is safety part, and then we can just run CFD and save those data on those computed nodes. Okay, and for experimental study part, we use PIV to record the flow field, and we use force sensors to record the force, and we monitor the power input to record the power consumption. Okay.
Okay.
So
Thank you.
if you want to do the research in this field, or you have any concerns, and you might send me, and you might see how we can work together or how I can help you, or our students can help you.
Yes, sir. Yes, sure.
Okay.
Thank you.
Well, thank you so much for the great talk. Thank you everyone for joining. And I guess we end the seminar here, and thanks again.
Thank you. Bye.